Okay, so we said that. So I started both recordings and I see them now. Okay. Okay. We said that it would be nice to have more than one linear space, one for the instructions and one for the data. If we do this, then we will have the twice the amount of linear memory. This used to be the case for the old computers, because in the old computers maybe 64K of virtual memory is not enough. Nowadays this is not a problem, because Intel architecture, 64-bit stuff. The architecture lets me um, address this much of memory, 2 to the power 48. Okay. Uh, this much memory can be addressed, no problem. So I wouldn't have this problem of having too small linear space of virtual memory. But nowadays they use this idea, separate instruction and data spaces for the L1 cache. Okay. That's the idea. If we have two spaces, I and D space, then one is for the instruction, the other one is for the data. They can grow and shrink, and I can use whatever I want. Okay. Remember, this is paging, and in for the page. Okay, question. Maybe I shouldn't tell you this. If I do this, if I do this, okay, let's say this is 2 to the 32. Okay, that means I have uh, 2, okay, this is 2 to the 32 kilobytes of space, linear space for me. If I divide this into two, okay, one is for the I space, the other one is for the D space. How about these two empty spaces? Am I not wasting these empty spaces? It looks like I am wasting these empty spaces, right? Are they wasted? Previously, even if I am wasting something, I mean, I would have wasted at most 2 to the 32. Now I am running into this problem. I am wasting space. Any answer? We can have more data and more program space. They can be useful. No, we don't keep. What, Hussein? What do you mean by that? No, we don't keep anything there. Well, I mean, if you don't keep anything, that means wasting, right?
No, we don't waste
What do you mean you don't waste?
uh, because we only use instruction and data part. Spaces
Yeah.
are not there, so they are not wasted.
This is your memory, okay? You are using only this part of the memory, but not this part of the memory. So this part is wasted. Nobody is using it. It is empty. I think if they are not full, we are not wasting it. What do you mean, Doğancan? I mean, if you have total of 64 kilobytes of space, okay, and if you are not using 48 kilobytes of it, then you are wasting it. This was enough for me, okay? This space was enough for me. My data and my instructions are fit together very nicely. I separated them into two. Now I have this much empty space and I have this much empty space. Okay, I have this much empty space in the D space and I have this much empty space in my I space. Okay, so isn't this waste of space? Can we use iSpace for another process? So I mean, if you are going to make those kind of beta, if you are going to make those kind of solutions, why don't we use this solution then? I mean, this was good enough. I share my space with for data and programs. So this is a fundamental problem that is addressed by the paging actually. Remember, we are using paging. Just try to think about that. We are using paging. So try again. Think about paging. We are using paging. This space, I space, and the space, they are all both paged. It means what? All those unused spaces, all those unused spaces will not be in your memory because they are not referenced, they are not modified, right? Okay, so they will not, you will not keep them in your memory. Okay, well, you might say that, okay, you are wasting this space then. Well, we have some solutions for that. I mean, if you are not using some spaces, then you don't keep them anywhere. Okay, so if you are using paging, I mean, otherwise how would you say that you have 2 to the 48 2 to the 48 bytes available for you? Because most of the space is not used, and most of the space do not occupy any place in your memory. Okay, because you don't use them at all. Okay, and your operating system is smart enough to keep all those unused pages because they are not referenced. Okay, they are not modified, so they will not be in your memory. Okay, okay, let's move on then. Is this clear? We understand it. So paging is very something beautiful. Okay, with the paging we have solved many problems. Okay, we solved compaction problem, we solved the memory allocation problem, and we have solved very large programs not fitting into memory. Also, we have solved this problem of small program not using the whole available space. Okay, good. If there are no questions, then I will continue in this case. Remember where we are now. We are here. We said that we we did this. Okay. We try looking at the design issues of the operating system regarding the memories. We first looked at the algorithm versus allocation. Is this something local or global? Okay, we looked at that one, and then we looked at swapping. Should when the page force goes so high, then maybe I should swap the whole process to the disk. That's the second thing that we looked at. Then we said that maybe who is controlling the swapping? Maybe there should be a second level scheduler for the swapping. We talked about that. Then we talked about the page size, and we had a simple calculation. And then we said that there is this idea of separate I and D spaces. Again, this is not used much today. It is used for the organization of the L1 cache, but we will come to this idea later. Okay. Now we are looking at the shared pages, and I think we talked about this a little bit before. Now we are going to look at it in more detail. So think about what happens after a fork. What does the fork system call do? The fork system call just copies everything in that process. It makes a new process. They are exactly the same. Only the return value for the fork system call is a little bit different, right? So Yusuf, we don't talk in Turkish in this class. So how do I delete this message? Yusuf, delete your message, okay? Either write it in English, okay, or don't write anything. I think I can delete this. Do this, do that. Okay. So after the fork, we see that there are two processes in my memory, and they are very similar. They are exactly the same. So if we had used the separate I and D spaces, then I could have done this. This is the picture. I have two processes running, but their instruction space is the same. See, their instruction space is the same. Their data spaces are different because they modify their data spaces, but they don't modify their instruction spaces because instructions are fixed. Okay, so that means that if I had this option of shared pages, then I would have shared my instruction pages with all the processes that I have forked. Okay, so this is the idea of shared pages. Sometimes if you share pages between the processes, you will be fine. Remember, our page tables are like this. Let's say this is my memory in the middle. Okay, these are my page frames, one by one, and this is my process number 1, and this is my process number 2. Let me make this process number 1 a little bit, okay, same size as process number 2. Okay, so this is the page table, this is page table, again this is page table 2, both of them, and these are my virtual pages. I might say that, okay, this one points here, this one points there, this one points there, this one is not here, not there, but this page and this page might be pointing to the same page number, okay, and these are not in the memory. Okay, so this is my physical memory in the middle. The rest, the two other are the my processes page tables, and this box, this page frame that I marked with the green color is shared. Okay, so if page sharing is possible, I could have used it with this kind of for this kind of efficient architecture. Okay, process architecture. Share some instructions. Okay, so that's the idea of shared pages. This would be possible for the I and D space. Can we do this with the D space? Can we share pages for the data spaces after the fork?
We can't.
Just explain. You can't. Just explain it a little bit. Why?
Because two processes operate on different data.
Yeah. Well, as long as they read it, it is fine. But when they start modifying it, it will be a problem. So it will be a problem if they start modifying it. They say that maybe we could do this. Sharing data is not that easy, but it is not impossible. Okay, so what you need is only the data pages that are actually modified need to be copied. Okay, only the data pages that are actually modified need to be copied. That means that as long as my modified bits are not 1, then I should keep using the same pages because I'm just referencing it. As soon as I made my first modification, then I copy that page. Okay, I make another copy of that page, and that will be my copy. This approach is called copy on write, and it's a important technique to make efficient use of data between two processes. Okay, so even with the data, if we are careful, we can find some solutions. Okay, so we have a question. Selman has a question. If you use execv, want to change the instruction. Well, I am not talking about execv. I am talking about a fork. Yes, for the execv, of course, everything changes. If you are changing your core image, of course, everything changes. There is no doubt about it. Okay, good. So copy on write is a technique that is used. We don't know. We don't know. I mean, let's first start sharing the pages, data pages. I don't know if I'm going to modify it, but as soon as I modify it, the operating system will automatically make copies of the modified pages, so I have both. So maybe some part of the data will stay the same. It won't change at all. Okay, so I will keep using the same memory. So that's efficient use of memory. Also, that will lower the cost of context switching too. Okay, context switch overhead can be reduced because why? My address space, of course, between two processes, address spaces are different, but if most of it is the same, then context switch time will be shorter. Ihsan's question is copy and write a regional thing or includes all the program. No, of course it is done by page by page. Okay, so these are two data. Let's say at the beginning of the program, okay, let's say at the beginning of the program, at the beginning of the fork, both the instruction pages and the data pages are shared with the green arrow I showed you, with the green arrow. So I am sharing both the data and the program at the beginning after the fork. Let's say I have modified one of the pages, then I will just copy that page to a new space and update my page table of that process to reflect this change. Okay, so that's the advantage of paging. Okay, you do your processes on the pages, so copying is done page by page. If you copy the whole program's data space, that would be expensive, and frankly that wouldn't be that different from copying the whole data space at the beginning of the fork. Okay. Good. Let's move on. Then we will come to this idea of shared pages, and we will talk about this a lot because we are using this a lot actually. Okay. Shared libraries. Remember the DLLs. I think you had some exercises in your object-oriented programming or other programming courses with the shared libraries. Shared libraries. How many programs in my Windows computer is using this function printf, do you think? Printf. Okay. Printf is a very common function. It is used by many C programs. And if I have more than 100 processes running, or maybe let's not talk about print because printf uses the terminal. Let's talk about fopen. How many programs do you think they are calling this function fopen? It's a program that makes a system call, etc. But it's a function, right? So it has to be called. If each program that calls this fopen includes the fopen code in their process instruction space, that would be waste of memory. Okay, that's why they say that let's make this into a shared library Okay, let's make this to a shared library. Whoever wants to use this function, okay, they should share that library in their page tables. Here's an example. This is a page table for the process 1 on the left, and on the right there is a page table for process 2, and process 1 thinks that it keeps, okay, the code for these standard stuff for, let's say, f open, printf, what else, strcmp. Okay, the code is available at these pages. Okay, the same type of functions will be used by process 2, and process 2 would think that they have those code available in these addresses, but in fact in the physical memory I keep them at the same shared pages. Okay, so the code for these fopen, printf, strcmp will be shared by many processes. These are called shared libraries, or in Windows we call them dynamically linked libraries. Okay, I think we have a question there. What if Salman is a question? What if a reference memory changes? Will it detect that as modified too? Well, a reference memory cannot change. What do you mean? Reference means that you are just reading it. Modified means that you are modifying it. Okay, and the CPU and the memory management unit is responsible for detecting modifications and the references. If I am reading a memory location, it is reference, it is not modified. If somebody else is modifying it, it is the responsibility of that process to make a copy and use that copy after that. I will not be affected. If I am just referencing it, if I am reading it, I will be fine. But if somebody else is modifying it, then that person, that process is responsible from making a copy and modifying the copied version. Okay, Salman, did that answer your question? Okay, so this is the idea of the shared pages, shared libraries. Actually, I mean, shared libraries are kind of versions of specifications of specific. They are specialized versions of the shared pages, shared memory. Okay, so we share the libraries this way. But the thing is this. The thing is this. Okay, let's think about a function in the shared space. Let's say I have instructions like load something, store something, and maybe I should jump to address. Where is this address? I don't know. Let's say this address is 12k. Jump to address 12k. Okay. So if I use these kind of absolute addressing, let's say jump to this address 12k, that would be very confusing this program, also for confusing for this program, because this address is not valid in this virtual address space or in this virtual address space. Even if it is valid, that's a nonsense address. So what are we going to do? The solution is use position independent code. Use position independent code. Position independent code means that nobody refers to any memory location by the absolute address, but relative addresses. You don't say jump to jump to 12,010 address, but instead you will say jump relative to minus 100. That means that jump to a location that is 100 bytes below me. So all of your addressing would be relative addressing, and this kind of addressing is possible with many CPUs. Okay, Ihsan has a question. Are all DLLs loaded to memory at the start or OS loads some of them when program needs? Of course, they are loaded whenever they are needed. If nobody is using this fopen function and the shared library that includes the fopen is not in the memory, the first time I call that function fopen, okay, that page has to be brought in from the disk to the memory, and operating system is responsible for that. That's why the first time you make a function call to a shared library, it will take more time to load it. If I had to keep all of the DLLs in my memory, okay, if I had to keep all of the DLLs in my memory, then would have been very, very expensive in terms of memory usage. Where are the DLLs on my Windows computer? The DLLs are, I mean, if you look at the DLLs, can I find it? Maybe just go to where is this computer, and here, and in my Windows directory, and inside the Windows there is this system32, and inside the system32, see, these are all the DLLs, and some of them are very large, some of them are very small. So if I had to keep all of these DLLs in my memory, then I would be in trouble. And these are not all the DLLs that I have. Okay, there are many other DLLs. Okay. So Ihsan made a calculation. He said it is about 25 gigabytes, and that's a lot of. Well, most of them are paged anyway. They are all paged. That means that you don't have to load all of them at the same time. But even a single page from each DLL makes lots of memory. Okay. So the operating system has to be smart about loading DLLs. Okay, good. So shared libraries are paged again, and when you write shared libraries, all the addressing are done relative position independent code. There is no absolute addressing. Okay, so another design issue or the feature with the memory is the mapped files. Okay, files, as you know, they live on the disk, on our secondary storage. Okay, most of them is a disk or some kind of a solid state drive, but they are not in our main memory. There is a system call in Linux or Unix variations. It's called memory map. You could map a file to your memory. It looks like this. I will try to make a picture of it. This is your, if my pen works. This is your memory, and this is your disk. On your disk there is a file. Okay, a file. When you make this system call, map this file1.txt to my memory location between starting this address 0x85AC. Okay, so the operating system makes the bytes of this file available starting from this position to the end. So any program that reads this address, okay, that reads this address, will read the beginning of the file. So you are mapping your file to the memory. Of course, this is done using paging. You don't have to bring the whole file to your memory. Okay, you bring it page by page. If some of the pages are not used, you don't keep them in your memory. Okay, so this is one way of doing input output actually. Instead of going to the desk, okay, opening a file and closing it and appending and doing that kind of stuff, you modify your section of the memory, and operating system handles the communication between your mapped memory position and the file itself. Okay, this is a convenient way of doing input output with your secondary storage. Okay, instead of doing reads and writes, they can be accessed as a big character array in memory. And actually the shared libraries are done this way. Okay, when you load a shared library to your memory, it is a memory mapped file. Shared libraries are on the disk. Okay, you memory map them to some specific positions in the memory. Operating system does that actually, and you continue using them as your instructions. Okay, remember the DLLs, they don't keep their data in themselves. You keep your data in your stack. So DLLs, they use only instructions. They don't contain your stack space. Okay, if you share a memory mapped file, okay, then that means that two processes are communicating over a file. So this is one way of making a communication between two processes without using any disk input output and that kind of stuff. You are using your memory. So you are mapping file to some memory location and you are sharing those pages between the processes. Okay, so two processes can communicate over shared memory that way. Okay, any questions so far? Good. Let me get some water. Yusuf, that bird was fine actually. Why did you stop it? I was hearing. Whose bird was that? Somebody's bird was singing. I mean, if it is okay for you with Yusuf, then I would rather listen to it.
Okay.
Who is the owner of the bird? Okay, they're shy. Okay, if there are no questions, then I will continue with the mapped files and. Okay, so far we assume that demand paging, with the demand paging, if there is no page available, then I will replace one of the occupied pages. Okay, before that there is a question: what is the difference between map files and named pipes? Well, map files, memory mapping, okay, file mapping is a system call, and you could implement the named pipes with the map files too. Okay, I'm talking about what Ozan is asking is a specific Unix question. Okay, named pipes or any pipe could be implemented using these techniques. Okay, these are specific names given by the Linux or Unix to some techniques. Okay, for example, in Unix, in Windows, okay, we call them DLLs. In Unix environment, we call them shared libraries. Okay, they are using the same idea. Okay, so named pipes can use can be implemented using the memory mapped files. Okay, so we assume that so far, whenever we need a new page, okay, a page fault, I need to load a new page. I need to make a page replacement and select the page and load it that way. That was the idea, but it is not the case in real life. In real life, we know that paging works best when there is a good supply of free page frames. Okay, if there are many page frames available, okay, loading a page from the memory, from the disk to the page would be so fast. I don't have to spend time. I don't have to spend time to look for a available page frame, to write it. If I need to make a replacement, I need to maybe write that page to the disk. I have to wait for that. That would take lots of time. We don't do that, okay? Usually what we do is we keep maybe 20%, 30%, 40% of the pages available. As soon as a new process needs a page, I just use one of the available pages, okay? So what happens if I have used more than 80% of the pages? I have only 20% of the pages available. So for that case, operating system says that I have a special process called paging daemon. Okay, it's a special process. It just sleeps like the daemons do. Okay, it's a special process. It wakes up if the available page frame is less than 20%. It says that I will select some pages and I will write them back to the desk if they need to be written. So I will run the page replacement algorithm before I need those pages. Okay, so that I keep a good amount of abundant amount of free pages available all the time. This is called cleaning policy. This is the experience from the operating system designers. If they do it that way, then I will be fine. When you look at my task manager, okay, for some reason everything became Turkish on my computer. I don't know. Is everything Turkish? Really? Yeah, everything became Turkish. Some of them are. This is en son eklenenler and this is productivity. I think it will take time to make everything Turkish. So if I look at my task manager, okay, it says that I am using 67% of my memory now. 30%, 33% is available. But if this number gets up to 80%, I will feel my computer is sluggish because I will have lots of page faults and those pages needs to be replaced and that kind of stuff. Okay, since I don't have enough space available. If the space is available, just load those pages and continue. If the space is not available, then I have to run the both page replacement and the allocation of the new pages. Okay, so don't keep this number high. Always keep this number below 60%, 70%. Okay, now I am around a critical value. If I run something else, then I will be in trouble. Who's using my memory? The stupid Teams, and I don't want to call OBS stupid because it is free, and Robot is stupid too because I paid money to it. Okay. Good. So this is the cleaning policy. Kamil has a question. So paging daemon finds the empty frame, so there is no overlapping between physical address spaces. Paging daemon doesn't find the empty phrase. It just does regular page replacement. It says that if I need a new page now, which page would I replace? It finds all those replaceable pages and it makes them available. It doesn't make a page replacement. It just marks those pages as available. It doesn't replace that page with a new page from the disk. It says that, okay, nobody is using this page. Okay, nobody has been using this page recently. So I will mark this page as page frame as available. So this is what happens with the cleaning policy. Operating system, of course, it plays a central role with this paging. It is all done by the operating system. We mentioned this a few times, but the regular programmers, users, they don't know anything about paging. They think that they have one nice linear address space. Okay, I could keep my instructions and data in that linear address space, and that address space is very large, as large as this big. Okay, on Intel architecture, and I don't care about the rest. If the memory is enough or not enough, I don't care about the rest. The rest is handled by the operating system. So the operating system is involved with the paging at 4 different main positions. The first time is, of course, the process creation time. When the process is created, like we create an entry for the process table for each process, I need to make a new page table. Each process should have its own page table. Okay, each process should have its own page table. So that page table is created, and the space allocation is done for that page table. Also, space allocation has to be done for the pages of that process. Okay, at the beginning, only a few pages will be allocated, and when the new program starts loading, it will cause many page faults. Okay, many page faults, and it will start loading its working set in the memory. So it will take some time to get up to speed with the new process. Okay, I think Kamil is asking another question about, I think it's a follow-up to previous question. So how unique pagings are supplied? Kamil, I did not understand this question. What is unique paging? Okay, maybe I should draw it this way. This is your physical memory, right? Green. There are some pages. Okay, this is my on the left process number 1, and this is on the right process number 2. Okay, process number 1 says that I am using this page. This one says I am using this page, and this page. Okay, this paging daemon makes sure that there are always more than 20% of the pages available in my main memory. So in this case, I have total of 6 pages, and 2 is available. Okay, 2 over 6 is a good number. Okay, let's say if I am using this one too, now the available pages is down to 1. Okay, down to 1. This is not good. So the paging daemon will kick in. It will say that I will get rid of one of the pages from this memory configuration, and I will maybe make this available now. Now I am back to 2 over 6. Okay, this is what is happening with the paging daemon. Paging daemon always keeps some of the memory pages available, so that if a process needs a new page, it doesn't have to look for a page to replace it and use it. It just uses it. It does uses one of the available pages. Okay. So let's look at this again. Four times when the operating system has paging related work. The process creation time, page table is created and space allocated. During the execution, when there is a context switch, okay, first of all, during the execution, when I access my memory, okay, when the CPU says that I am going to write this value to this memory location, operating system is not involved at all, because memory accesses is handled by the memory management unit, right? Memory management unit makes that address translation from the virtual address to the physical address. So every time I make a memory reference, memory modification, MMU handles that address translation and changing the reference bit and the modified bit and etc. So during the regular execution time, operating system is not involved because the CPU has the process has the complete control of the CPU. But if there is a context switch, then that means that my TLB configuration has to be flushed and MMU has to be reset, because MMU is going to be used by some other process right now. So all the registers in my MMU and all the values of in my TLB has to be changed. Okay, TLB is not valid anymore; it is flushed, and my page table that is pointed by the MMU registers, they all have to be reset. Okay, so this is the second time during the execution of the program operating system is involved with the paging. Okay, so this is the second time. Again, this is very important. Operating system is not involved during the regular execution of my program. Every time I make a memory reference, memory modification, okay, all the address translation is done by the MMU. Operating system is a piece of software, okay. It is too expensive to run the operating system for every memory reference. That's why operating system is not involved during the regular execution of the program. Okay, so this is the second time. I think I am out of time. Maybe if you have any questions, I will get a question first, but after that I will get a break of 10 minutes. Any questions? This captioning works very well. Most of the time it gets whatever I am saying right, even though I am not using the correct words, correct pronunciation. It gets most of the time from the context. Any questions? Okay, then 10 minutes of break. It is 11:24 now. Let's be here at 11:34. 11:24, 11:34. Okay. Okay, let's start. So we said that operating system is involved at 4 different places regarding the paging related work. The first is the process creation time. The second is during the execution. If there is a context switch, then I have to do the MMU reset and TLB flash. That will take lots of time. And of course, page fault time. If a process says that I need this memory location, and MMU says that that memory location, the page that contains that memory location is not in the memory. So I need to make a page replacement, find the available page if it is available. If the page is not available, then I will need to make a page replacement. Okay, so a page replacement and finding the page number that caused the page fault is the responsibility of the operating system, of course. And then the last time is the process termination time. Okay, process termination time. When the process is terminated, all the page tables has to be released, and the process should say that, operating system should say that whatever the pages are being used by this process, they are now available to be used by anybody else. Okay, so this is an important step, because if you forget about your pages and if you don't mark them as available, then they will be kept as allocated memory. That's not a good thing. Okay, Ilhan says that the attendance is out now. Okay, so you just fill in the attendance. Okay, good. Any questions about the operating system involved with the paging? Of course, this did not assume this discussion did not include paging daemons. Remember the paging daemon? Okay, so paging daemon, it comes from time to time whenever there are no sufficient number of pages available. It comes in and it kicks in and it will make these arrangements. It didn't talk about it, so it is, I mean, these 4 points are the points of a life cycle of a process: process creation, process execution, fall time, and the termination time. Paging daemon is not dependent on the project process life cycles. It can kick in any time, even if there are no processes available, user processes I mean. It may kick in and it will do some housekeeping stuff. Okay, good. So this is important. The third one, page fault, is important. Let's look at what happens with the page faults. Whenever a page fault happens, let's follow the steps that the operating system takes, or not the operating system, the whole computer system takes, because some part of it has not anything to do with the operating system, but some parts are 100% operating system. At the beginning, okay, I execute an instruction that needed to access a memory location, okay, and MMU said that I cannot make this translation because because this address is not in the main memory. Okay, so it causes an hardware trap to the kernel. Okay, so I said this number one is completely hardware thing. It has nothing to do with the operating system. It is all done by the hardware. Okay. Okay, Fırat, please ask these kind of questions at the end of the class. Okay, I'm trying to discuss something. The hardware trap is created. And this is done by the hardware itself. And the hardware says that there is a situation and I will save the program counter on the stack. That's what it does, and it causes a trap to the kernel. Then the operating system takes over. Operating system takes over. Operating system says that operating system says that I will save all the general registers, any other information that may get corrupted if I run too long, and then after that I will start handling this page fault. Okay, page fault means that I am trying to access some memory location. That memory location is not in the memory. Okay, and then I discovered there is a page fault, and the first thing to discover is which page is causing this page fault. Okay, that's an important thing. Okay, trying to understand what page is needed, and obviously that page is not in the memory. Okay, once the virtual address caused this fault is known, I know the page number now. Okay, so the system immediately checks to see if the address is valid. I mean that might be an invalid address. I mean that might be a very bad address. Okay, address that is out of your access privileges, or maybe you are trying to write to some location that is not writable, that's not modifiable. Maybe a read-only instruction page, you are trying to write to a read-only instruction page. So it checks to see if the address is valid. Also the protection is consistent with the access. Okay, so the number 4 is that one. If it is okay, then that means that it's a regular page fault. Then I will have to handle this. Okay, so then when I know that I need to make a page replacement if I have to, and if the page to be replaced is dirty, then that page has to be dirty, means that it is modified. That page has to be scheduled to transfer to the disk. Okay, so this will take a lot of time. So while this is happening, I ask the operating system, as an operating system, I ask the other services of the operating system to make this disk transfer for me, and I will suspend the faulting process. Remember, there is a process. That process is trying to modify some memory location or access some memory location, and that is not in the memory, and I am trying to handle this page fault, and as a result of this page fault, I need to write a page to the disk so that I make a page available. So this will take time. That means that the faulting process, page faulting process, has to be suspended because it is waiting for some page to be written to the disk. As soon as the frame is clean, that page is written to the disk, the frame is available. Okay, then now I have to load that page from the disk to the memory. Okay, so it will be another disk operation schedule, and my again faulting process is still suspended. Okay, so whenever the disk driver says that the page that you are loading is available with an interrupt, then operating system kicks in again, and it updates all the tables saying that I have loaded this page is available, and I will mark the processes page table, also the TLB, okay, to point to this page now. Okay, so I did that. Now page is ready in my memory, and I updated all of my page tables and the TLB. And then I had to find the instruction that caused the page fault, and I have to do this backing up stuff. If I have an instruction, let's say I'm executing an instruction, and that instruction is making a few memory references, page fault may come from the instruction reading itself, or page fault may come from the instruction trying to read or write to a memory location. So I need to find the exact reason what happened. Okay, this is called backup, and we will talk about this in a few minutes. And after that, I found it. Okay, I said that okay, the program counter actually should be this, and I will start executing that instruction again. but that doesn't mean that faulting process will begin immediately. That faulting process is scheduled. It is put in the ready queue. Okay. When it is in the ready queue, everything is ready and the program counter is reset for that one. Okay. When the operating system thinks that it is time to switch back to that process now, it will be switched to, and it will load all of its registers and state information, etc., and it will start running. So this is what happens with the page fault. As you see, it is not a cheap thing. It is almost as expensive as context switch. Well, actually, a context switch is happening. Why? Because if I need to load a page from the disk, that will take lots of time, millions of clock cycles to load that page from the disk. So my process will be blocked for a while. While my process blocked, maybe some other process can run. That means a context switch. So page fault is as expensive as context switch. So page handling is something that has to be done very carefully. How often does page fault occur? At the beginning of the program, it occurs a lot, because at the beginning of the program, nothing is in the memory, right? Every page that you are trying to read will cause a page fault. Okay, this will continue until you reach your working set. If all of your working set is in your memory, then you will be fine. You will start running it. And after that, it comes to how full your memory is. If your memory is available, you won't have many page faults. Okay. So at the beginning of the program, there will be lots of page faults. At the end of the program, there will be lots of page faults. But if your program is an CPU bound program, it keeps its life. Okay, it spends its life on a very tight, small loop. Then that means that it keeps using the same pages over and over and over again. For that page, there will not be much page faults. And if your program is an IO bound program, that means that most of the time it is suspended. When it is suspended, it is likely that its pages will go away because some other process will use it. Okay, so when it is loaded back in, it will have to do some loading back to the memory. And in fact, you can measure the page faults using your task manager. I think you could add this page fault. You could add this page fault numbers to this table, I think. Let me see if I can find it. Do you know how to add the page faults to this task manager? Page faults. I think. What is this? Oh, okay, so it is just threads or the sub processes. I think there was a place where you could view the page faults. Okay, this is just talking about CPU usage, GPU usage, Wi-Fi usage, and okay. This one? I don't know what it says. I don't know. I need to find it. I know Windows makes this available, the page faults for each process, and you could make a graph out of it, but I don't know how to find it. For this, so Ozan has a nice command line. If says ps minus o pid min fault and max fault cmd. Okay, min. Are those, Ozan, are those command names? Okay, so for I don't have Linux. If I type that in on my Linux emulation, I don't think that it will show up. But for Windows it is available too, and I don't want to write it in, I don't want to spend time on it, so you find it. Perf monitor Gebze. Ihsan says that performance monitor. Okay, I am running this performance monitor. Okay, I loaded it, and there is this performance tracker. So it is giving me this, what? It is giving me is this CPU usage? Maybe I can add more stuff to it. So this is CPU usage. I think I can add more stuff to it. Let's add more stuff. So Ihsan, how do I add the page faults to this graph? Ihsan, how do I do that? How do I add the page fault? Yeah, Ozan, please upload the page fault image. But that image should be from the beginning of a program execution and at the end. There is this, what is this stupid, what is Lustiver? Okay. Maybe right click, yeni, görünüm, özelleştir, maybe ya. No. Okay, you figured it out, okay? I don't want to spend my time on it, but it should be available. Okay. So there is no way that you can avoid page faults, because page faults is a part of the picture with the virtual memory. Virtual memory means that you are using much larger memory than the physical memory allows. That means that page faulting is not avoidable. Okay, you have to have page faults. The important thing is that you shouldn't have many page faults while you have available memory. If you are making too much page faults, too many page faults, then that means that probably you are trashing and you should swap some processes out. Okay, Ozan sent something. That link has expired. Okay, I am just okay. You figure this out and you try to find how the page fault changes for the complete life cycle of a. Mohammed sent a picture, and that picture is okay. It's in the resource monitor. Open resource monitor, then this memory, and there is this hard. What is hard F? This. I'm going back. Okay, I don't want to spend time on it. Okay, you guys are tricking me. Whatever you send, I just click on it. Okay, so you figured it out. So let me go back to my slides, and this is how you handle the page faults. And operating systems is involved. As you see, it may involve writing something to the disk, scheduling a disk write, and it will involve reading something from the disk, another disk schedule. So it will take some time. It will take time, and sometimes it will be longer than the context switch time. So instruction backup is what I meant by this step number 8, instruction backup. Let's say I have this instruction being executed. I'll show you the okay. this instruction being executed. It has 3 bytes. This is the opcode for the move, and it says that move, okay, contents of this memory location to this memory location. It's a Motorola 86000 instruction. Okay, so it's a total of 6 byte instruction. Okay, it starts at address number 1000 and it ends with address number 1005. Okay, so it's a 6 byte instruction. When I am executing this instruction, this byte, the byte number 1000, might be in the memory. The next one might be in the memory. Byte number 1002 may not be in the memory, or byte number 1004 may not be in the memory. Okay, so there are many cases where the page fault can happen. Okay, the page fault can happen because some part of the instruction is in the memory and some part is not. Page fault can happen because the memory that is referenced by the instruction is not in the memory, or the second part may not be in the memory. So there might be many different cases where this instruction is causing the memory faults, page faults. Okay, so it is important to know which one has caused it, so that I would know the page fault, the page that is need to be loaded. Okay, that's one thing. The second thing is that the program counter is at the beginning is 1000. Okay, you increment the program counter to get your addresses. So when the page fault occurs, your program counter could be 1002 or 1004. You may not know that. Okay, it depends on the architecture. Okay, so instruction backup means that you need to figure out where your PC state when the page fault has occurred. Okay, and you need to recover that number, and when you come back to this program after the page fault is handled, you need to start from a consistent state. Okay, you need to start from a consistent state. That's what instruction backup means, and the book has a very good discussion. It talks about it, and it says that it is not an easy thing, because the author of the book, Tannenbaum, he writes his own operating system, Minix operating system. He's aware of these kind of problems. I mean, on the book it's just 1 or 2 pages of discussion, but when you try to implement an operating system, it will take lots of effort, lots of code. Okay, good. So people are talking about those page faults. Okay, hard faults, that's good. Yeah, okay, good. With the instruction backup, I think this is all I need to say. Let's move on then. It's an important thing, but I mean, there are no standard techniques to handle this instruction backup problem. You will have to use lots of tricks, lots of hacks that is related to CPU structure. Okay, there might be some hidden registers that is only available to the operating system, that will help you to tell you where was the last program counter is when this page fault has occurred, and etc. So you need to use all of those, but they are not relatable operating system concept discussions. Okay, they are specific problems, technical problems. We will not go into those details. Okay, another concept with the memory management is locking pages. Sometimes you may need to tell the operating system that this page is important, don't swap it, don't write it to disk, always keep it in the memory. So this happens in this case. Let's say I have a process, I have started an input-output request with the operating system. After that, I just blocked because getting the data from the disk will take time. Since I am blocked, I am not I am not using my pages, right? Those pages will get old, will get aged. Okay. When my pages, when my data pages get old, they might be replaced. But if they are replaced, that means that the buffer, my buffer that will hold this data may be replaced. Okay. So I asked the operating system to load some data, and I told them that whenever you load that data, put it in this memory location, which is mine. But since I am blocked, operating system may decide to replace that page that holds the data, okay, the buffer. So I may have to tell the operating system that although this buffer location will not be used for a second, which is a very, very long time, okay, its data, whenever its data is available, it has to be here. So I say that I will lock this page. Don't change it, okay? Don't change it. Of course, this requires some special privileges, and users don't have these privileges. It's a system level optimization, but this kind of a mechanism should be available for the operating systems, okay? Or instead of doing your input output in your user space, maybe all the input output can be done in the kernel buffer still, but again, those pages should be locked, should be pinned. This is what we call locking pages in memory. Okay, and as I said before, this mechanism is not available to the end users. Otherwise, end user would have said that keep all of my pages in my memory. So that would be a bad thing. Okay, so one important thing is that we always said that if I am replacing a page, I will write the dirty pages to the disk and I will load the new ones from the disk. But we never talked about what happens on the disk. How do I keep them organized on my desk? Okay, on my secondary storage. The idea might be this, okay. Picture from the book. Okay, in my memory, in this, when you look at this picture, by the way, how is my synchronization problem today? Is it same? Is it better? It is worse? I think most of it's good. Kevin, it is always good for you. Same, it is better. Some people. I think we figured out that this company Microsoft, they wrote their clients more optimized for the Windows environment, but their clients is not that good for the Linux environment. Maybe for the Apple environment too. For the cell phone environment, I don't know. Is anybody following my lectures from their cell phones? Is the cell phone performance of Teams better, or is it about the same with the Windows PCs? Salman is using cell phone, and how about the synchronization? Is synchronization a problem with the cell phones? I feel it is like better. Okay, it is better. Yeah. Well, most of the world they are using their cell phone. Cell phone performance should be better. So it's a combination of both Microsoft stuff and the infrastructure of internet in Turkey is to load it. So I think I figured out how to handle this. I am trying to keep the pages same without making fast switches between the slides. So when we come back to this picture again, this is my main memory on the left. Okay, I have only 4 pages loaded, page number 0, 3, 4, and 6. Okay, 6. and these pages are available in the memory, but my virtual address space is how many pages are there from page number 0 to 1 2 3 4 5 6. There are a total of 8 pages in my virtual memory, so I keep only 4 frames in my memory. The rest is on the disk. So this is how you organize your disk on the right. Okay, on the right, page number 7. Okay, page number 5, 2 and 1 is on the desk, and the positions for the page number 0 3 4 and 6 are empty on the swept disk area. So that means that I will keep a swept area like this on my desk, okay, which looks like it is wasteful. Okay, why? Because on my Intel architecture, my address space is this big, right? It is this big. I need to keep all of this data, all of this large memory, 2 to the 48. Okay, I need to keep them on my desk. It is too big. Okay, I don't wanna do this. I don't wanna do this. The alternative is only keep, okay, the valid pages that are not on your memory. Okay, only keep the valid pages. So don't keep a fixed swap area. Your swap area will be smaller, much smaller. So it will dynamically get larger and smaller, but it will not be static, and it will not waste space. This is called backing store on your desk. And how you handle this backing store depends on your operating system. For example, Linux uses a separate disk area, physical disk area, a disk partition. When you install a Unix operating system, it will just keep some disk partition as a swap area, so that this loading pages and writing back the pages to the disk is fast. Okay, but it's a special area. Again, I need to keep this very, very fast. Okay, so everybody has their own idea of why this Teams is causing this synchronization problem, but yeah, well, we have to live with it for a while. Okay, so that's the idea of backing store. Simplest algorithm is to have a special swap partition on disk. Okay, the alternative would be allocate the space for each page when it is swapped out. Okay, whenever it is swapped out, I just write it to the position. By the way, I may not have to swap out any instruction pages. Why? Because instruction pages are not modified. Okay, they are the same as the original pages. So why don't I load them from the original positions, right? I could do that. Okay, so this is a very important optimization stuff for the operating systems. Okay, any questions so far? I will upload these two videos, the videos from yesterday's lecture, also a video from today's lecture. Today afternoon I am going to the school today. I will upload them to YouTube, and you may watch these videos from YouTube, because I checked the Teams videos. They are again laggy, and I don't see it very. I don't think that you can view it very well. So YouTube recordings are better. Okay, so let's look at this idea of separation of policy and mechanism again. We looked at this idea when we did the process scheduling. Remember, the process scheduling has two parts. One is the mechanism, How do I switch from one process to another process? Okay, that's the mechanism. That's important. But there is a policy too. I mean, sometimes it is the application that makes a decision to switch from one thread to another thread. Okay, so that's the policy. The policy might change from process to process, from thread to thread, of scheduling policy. Okay, and we say that maybe the same thing should happen with the page replacement or the memory management handling. Okay, what do I mean by this? Maybe for some processes, keeping a special page in the memory is important. Maybe the application knows what the working set is, and the application says that I am going to keep this many frames in the memory, etc. For this, I need to separate the mechanism of memory management from the policy of memory management. Okay, those two things are different. Okay, so let's look at the picture from the book. The picture says that, of course, I have the user space and the kernel space. In the user space, of course, I have my user processes, and if the user process is causing a page fault, there will be a trap to the kernel. Okay, kernel will say the program counter and etc. We have looked at it already. Usually we divide our memory management handling into three. Okay, one is the memory management unit handler. Okay, this one has to be definitely in the kernel space. This one has to have the special privileges because it is accessing the special memory management unit registers, like the TLB tables, its registers and pointers to the page. And the other part of the kernel space is the page fault handler. Okay, page fault handler. That page fault handler is responsible for doing whatever the operating system is doing when the page fault happens. We looked at those 8-10 steps of handling the page faults, right? That was the page fault handler. And we have the external pager. This external pager has the, okay, these two down at the bottom, okay, these two, MMU handler and the page fault handler, are the mechanisms of handling memory management. Okay, the one in the user space is for the policy, external pager. MMU handler is machine dependent. It has to know the details of the CPU and the memory management unit. Fault handler is not machine dependent, but it needs special access to the page tables, like the read, reference, and modified bits, right? So, but this is not page fault handler is not machine dependent, and of course the external pager, it doesn't have any special privileges. It is not machine dependent. It's a regular C code, okay, and it is responsible for getting the data from the disk and setting it up in the tables and telling the page fault handler that the data that you like to load is available now. Okay, the data that you load is available now. Of course, this one, external pager, does not have privileges, any privileges to modify the page tables. It cannot read the reference bit or the modified bits, right? So it has to communicate with the kernel in a very frequent way. Very often it has to communicate with the fault handler. So this is how you separate your policy of memory management from the mechanism of memory management. Okay, Emre has a question. What happens if step 4 doesn't return a page? You mean if the page that I am looking for is not on the disk? It has to be on the disk. That, I mean, When the page fault happens, it means that the page that I am looking for is not on the memory, so it must be on the disk because I had used it before. I know that it is in my virtual memory. If it is not on my physical memory, then it must be on the disk. If it is not on the disk, then there is a serious problem with my virtual memory management. It has to be there because I had written it there. Either it's a disk problem or there is a bug, very serious bug with the operating system. Okay, so let's go back and let's try to see what the book says. Okay, 3 modules: low level MMU handler, SMD, and machine dependent. Okay, the second one is page fault handler, that is part of the kernel. It is machine independent and it's a mechanism for paging. Okay, and the external pager is the policy and machine independent. That's the policy. That's the policy is the main logic that tells the memory management how to behave when it comes to do page replacements, when it comes to do optimization regarding the special process needs. Okay, without the mechanism, policy doesn't mean anything. Mechanism is important, okay, but mechanism is just a tool, okay, for us as a tool. So this policy manager in the user space is responsible for using that mechanism to implement an efficient, effective memory management system. Okay, and we had the same idea again. We had the same idea of separating policy from the mechanism when we did the process scheduling or the thread scheduling. If I leave everything to the kernel, if I let the kernel to do both mechanism of process scheduling or thread scheduling and or the policy management, it will do a good job, but it will not be flexible enough to meet my special thread or process needs. The same thing is here too. Okay, if I have special needs for the memory management as an application, then I need to have a mechanism. I need to have a external pager like this. And in fact, this makes everything more modular. If you like to take your memory management code to some other machine, all you need to do is just modify this MMU handler. Don't modify anything else. Okay, good. Any questions so far? Okay, so if you split policy from the mechanism, again, the external pager doesn't have an access to RLM bits. That means that either many switches to the kernel, or you will have to find some other way of doing it. Okay, it looks like a little bit inefficient, but it is more modular and easier to manage. Okay, the final part of the book talks about segmentation. Okay, again, we talk about the separation of the virtual space into this instruction and data space. Remember, we had two different linear spaces. Segmentation takes this idea and instead of using two different linear spaces, segmentation says that you will have thousands of linear spaces or tens of thousands of linear spaces. Okay, that's the idea of segmentation. The idea says that why do I have to have a single linear space? I like to have, as a programmer, I like to have many linear spaces, and I will treat them separately. Let's say you are writing a compiler, okay? You write a compiler, which is a very complicated piece of software, okay? So for the compiler, first you need to keep your source file in some place, your symbol table, your names, your attributes, and etc. in some other space, okay? Your constant in some other space, your parse tree, your stack, etc. in some other space. So this would be the picture. If you have a linear space, that started from address number 0 to some large number 0 f, right? So some large number. So in your program you have to make this arrangement. You will say that I will keep my symbol table at the top, then maybe my source tag, then constant table, parse tree, etc. The problem is you have to make all of these dynamic shrinking and growing procedures. You have to handle all of them yourself. I don't, of course, I mean, if there are no other solutions, then you will have to do this, but this is difficult. They said that why don't I get some help from the hardware? What do I mean by this? I will keep each of these different types of data or code in a different segment. So I will do this. Let's say I ask the operating system, give me 5 linear spaces, linear logical spaces. The first space will be 20 kilobytes long. The second will be 12 kilobytes. Okay. This one will be just 1 kilobyte. Then 16, then 12 again. Okay. And I will put my symbol table into first segment, second, third, fourth, and it goes that way. So each one is in a different address space, and each one has their own address number 0, address number 0, address number 0, right? So this is logically divided. This is logically dividing my program into 5. And as a programmer, I know how to divide my program into many smaller chunks, okay? Some of them will keep some data, some of them will keep maybe some special procedures. And if I need to make one of the segments larger, I will ask the operating system make this segment larger, okay? And if let's say if I make a mistake, let's say I said that for the segment number 1, okay, let's say I said I like to access the memory location 14K, and operating system will tell me that no, that's an illegal memory location for you. Okay, so error check will be better. So the idea of segmentation was available in 1960s. Like everything else, it started with Multics operating system. Paging has its roots with the Multics operating system too. Okay, so the segmentation is a special way of handling virtual memory. Instead of having one single large linear address space, you will have many address spaces. Each one belongs to you. If you like, you may share some of the segments with some other programs. No problem. But the user has to know about the segments. Previously with the paging, the user didn't know anything about the pages. It just said that I have very large memory. This one, the user says that I ask you, the operating system, I ask you to give me 5 segments, and each one is used for this and this and this purpose. Okay, so this number could be very, very large. As I said, I may have more than 256,000 segments, and each one can hold large amounts of data. Of course, segmentation is not used by itself. We page each segment. Each segment is page made. Let's say this is 4 pages, 3 pages. Okay, the segment number 3 is 4 pages. Again, it goes that way. So if you use segmentation with paging, if you say page each segment, then you will have the best benefit from both techniques. Okay, of course, segmentation has to be supported by the CPU. Like the virtual memory has to be supported by the CPU. Okay, segmentation has to be supported by the CPU. Okay, we will talk about the segmentation next week, and we will close up this chapter number 3, right, about memory, and I will start talking about our secondary storage. Somebody had a question about the homework number 1 grades. The grades are ready. Our TAs, Gizem and Ilhan, graded your homework number 1, but we are having lots of issues with the cheating. There are lots of cheating incidences, and we are trying to handle them. Okay, we will not tolerate any cheating. I think this is surprising for me this year. This many cheating happened, and we are trying to sort it out. Once we sort it out, we will announce the results. But I expect that the lots of people will be getting minus hundreds. Okay, any questions so far? If there are no questions, then I will stop here and we will continue next week. Okay, see you next week then.